Good morning, friends. I'm your friend Kumar again. So, in last session, I was discussing about how data actually stored in a column storage and how conversion works and how SAP HANA improves data fetching process. Today, I'll discuss data compression techniques. So, what are the data compression techniques we have? And because of that, HANA achieves performance. So, today I'll discuss in detail. So, before moving further, uh, if you are watching my video first time, so I would say go to my previous video first and understand how data actually stored in a column storage, because my next example, next discussion is based for the data compression technique is based on actually the format, the way data stores in a database. And if you understand that process first, that technique first, then you can understand how compression techniques works. If you're not aware how it works, so I would request all of you to go to YouTube and watch my channel. Just go to YouTube and write down SAPEX Technologies. You will see this icon, SAPEX Technologies. I have shared multiple videos here over SAP HANA. For the entertainment purpose, I have also shared one cube solving trick. So sometimes after, when you are getting bored with study, so you can try this video as well. And I believe in sharing knowledge, so I had knowledge of solving this cube, so I have shared this video as well. Apart from that, my objective is to share topics, share my knowledge over SAP HANA ABAP. So I will be sharing with all of you one by one. And I would try to publish my video every Saturday, so you can watch it, you can understand it, and you can practice it. So my topic is for today, data compression technique. So to understand this, you will have to go to YouTube channel and you have to watch out my previous videos where we have discussed how data actually stored in a database in a column store, how SAP achieves a column store process, and then only you can understand data compression technique. So let's move to next topic, next slide. So I mentioned it in my previous session. We learned about data conversion and representation technique in main memory, and obviously it was for column store, and how actually data gets converted and encoded in a numeric format using dictionary vector and attribute vector. So dictionary encoding is a by default encoding process in SAP HANA. So I have discussed it in my previous session, how dictionary vectors and attribute vectors get created, and SAP HANA actually stores a database based on store data in a database based on dictionary vector and attribute vector. So we also understood what are the various software components of SAP HANA, like HANA Studio, HANA Client, HANA DB, and software data for replication. So a lot of things I have discussed in my previous videos. So we also learn about how various data process, various process to access HANA DB, like you can access HANA DB directly by mobile device through internet, and what are the components involved in that. So I have also discussed it. Apart from that, I have also discussed how basis team actually works, how solution managers and software update manager works for the basis, and how mm, yeah, I would say HANA Studio is helpful for basis team or admin team for the monitoring and authorization purpose. So I have also discussed, not in detail, but I have discussed because that is the basis part. So I'll discuss here only things related to ABAP. So in my previous videos, I have also shared about data compression technique available with SAP HANA, which I will discuss in detail today. So I have mentioned here, um, I will publish my sessions recording in every Saturday, on every Saturday. So you guys can uh, access my YouTube channel, and I would request all of you to please like and subscribe it. So it will motivate me, and I can share more and more videos over SAP HANA, and I'm sure that it will be helpful for you. And I would say this is not the only videos which will help you. I would say practice at your end, and without practice, without looking into the system, you won't be able to understand. So I will show you how techniques works and everything in practical as well. Okay, so let's move to next slide. So in my previous videos, as I discussed various techniques about data compression, and this is the fact that data is stored as an integer format, and CPU loves processing integer values comparison to string and character values. So in previous videos, I discussed how actually mm, string or character values gets converted into integer format, and how actually it stores in a column format. So in a column format, actually integers are stored in a main memory. What is integer? Not the string, not the character, only integer. And traveling data from main memory to CPU becomes easier because of being integer. So if transferring data type is integer, so some advantages like lower storage requirements for values, so and fast data transfer, as I said, from main memory to CPU cache, and faster processing of integer values in a CPU. So we understand that we have a separate cache calculation area in CPU. We have gone through in our studies time, so we understand what are the registers and how actually numeric values gets processed in a CPU. So I'll not go into detail, but in a theory part we have learned that okay, CPU loves processing integer values. So based on this technology, SAP HANA uh, working and achieving faster data processing techniques. So there are like mm, multiple types of encoding, and before that I'll discuss about delta compression. So what is actually delta compression? I'll discuss it. I'll show you example how data compression works, and after that delta compression works for the attribute sorry, for the dictionary vector. And again there are various encoding process which I will discuss, and I'll show you practically like how like these prefix encoding, sparse, cluster, indirect, run length encoding gets converted, data gets converted into this encoding format. So that's why I said before moving further, in my last videos I shared about one hypothetical data I shared with all of you. Like we have a table in which Sumit Kumar, Shweta, Vivek Kumar, Athar, Vandana, Sumit, this is the data in my table, and it is being stored in a database, and in a column format. So how actually dictionary vector gets created, and how encoding works for the dictionary vector, how data gets converted. So I shared these are the dictionary vector, like for every column it creates one dictionary vector. You can see that dictionary vector name, dictionary vector location, dictionary vector gender, and it stores only identical records in a sorted format, and its position in a dictionary vector. And based on this position, if I sort this record, it will become like that. So this is the sorted data. After sorting, I have mentioned it. And after sorting, it is like this. And in a dictionary vector, it stores only identical values. So you can see that this is the identical values. So I discussed it in very much detail in my previous session. So before watching this session, I would request all of you to please watch my previous session. Then you will understand, because every time it's not possible for me to create this kind of data for you. My discussion will be based on this only. Main memory in a red color, you can see 1 2 3 3 4 5 5. This is actually stored in a main memory, nothing else. So like one, what is one? So you will understand in my previous video why this is 2, why this is 3. So you will understand in my previous video. And in my next example, where I will show you what is prefix encoding, sparse encoding, cluster encoding. So everything will be based on this structure only, because every time if I will create this kind of data, so I won't be able to cover everything. So instead of creating this record every time, I will assume that we have a table and data is stored in this format. So first you will have to understand what is this format, how it came into picture. So after that you can understand these encoding process. Okay. So before going forward, I was talking about what is delta compression. So let's see what is delta compression first. So delta compression is used for string s- strings in dictionary web. Okay, so this is used with dictionary vector. So in this kind of compression, what happens actually? Every character from a string, every character from a string in a block is stored only once in a delta string. So I think you won't be able to understand this. So let me show you in an example. Let me show you in an example. Like let me insert a text box here. What is delta? So let's give me one raw data. For example, you have a name like you have some value like brain, bus, Britain. So for example, I've taken some example. I assume that my data is sorted, and after sorted. after sorting any column, for example, name column or something like any column. So data will appear in this format. It's a dictionary process. So brain, bus, Britain, so and brush. So now after delta compression, what will happen? It will become like 5 brain, 12 US, 34 TAIN, and 34 TAIN, and it will become 23 USH. So how it happened? How it happened actually? So this is delta compression. So this is delta compression. But how it happened? Can anybody answer? No? So first digit, which is 5. First digit, which is 5, it indicates the total length of first character. After sorting, brain will be the will be at the first position, and the total length of brain is 5. So 5 indicates the total length of first character. Okay. Now 1 2 US. So I can see our next data is BUS, bus. So first character is, what is that first character? B. Okay, this is B. It has taken from here. So first character is B. So this first character is B, and there is two new character. Which one? U and S. Okay. Now next topic is 3 and 4. So why 3? So again, it is showing that 3 character is from here. Sorry, I misspelled spelling wise. BRIAN. This is the correct data. So first 3 character is what? BRI. So in this data we can see 3 character is BRI. So for that it has written 3 character BRI and 4 new character, and which is 4 new character? TAIN. So in this data first 3 character is from the BRAIN, and TAIN is a 4 new character. So because of that, this is 3 4 TAIN. Same way 2 3 USH. So first 2 character is from here. You can see BR is here. So first 2 character from the here BR, and 3 new character. 3 new character is USH. So I think this is the process how data compression works, and it converts all the string into uh, encodes the string into delta format. So any question? No? Yes, exactly. So what happens once we store any data? This is in a it might not be in a sorted format, but internally it's gets sorted, and after sorting any conversion works. So dictionary vector is a our default encoding process in SAP HANA. So guys, now look at the other encoding process. Other encoding process we have, for example, prefix encoding, sparse encoding, cluster encoding, and indirect encoding, run length encoding. So I'll show you one by one each encoding process in the same way. I'll try to make you understand in a same way which same way like we have discussed delta compression technique. So now if I look at the prefix encoding, for example, if I create one structure, for example, let me create a table. Let me insert a table with column. Let me create column of 20 and row 1. Yes, now this is correct design. So, for example, uh, we assume that we had a table in which multiple entries were was there, and after dictionary vector creation, data in a memory is stored in this format. For example, four, for example, four, 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 three, three, two, one, five, six, 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 seven, seven, eight, 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 nine. For example, after encoding and after dictionary encoding, so data in memory um, stored in this format. So, for example, there might be anything at the position 4, might be any name, might be location, might be anything. Any data can be here. But after looking at this data, we can understand that okay, 4 in a column, whatever value is stored, for example, SAP is stored. So SAP is stored 4 times. 1, 2, 3, 4. So might be 4 is for SAP and 3 is stored something like for example HANA. So HANA is stored 2 times, 1 and 2. So any data can be there. SAP, 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 HANA, HANA. So this is stored in a format. So for every dictionary, like for every data, there is a position, and based on that position, data is stored in a main memory. So how prefix actually works? So what prefix says? Prefix says identical values at the beginning of the attribute vector are left out. Instead, a value and the number of its occurrence is stored only once. Are you getting, guys? So after reading this, did you understand anything? So what it will store? Let me copy this. What actually what actually prefix encoding will store? I've just copied it. So what will happen in dictionary in prefix encoding? So how many fours we have? We have 4 fours. For better understanding, let me repeat it once again. 5, sorry, 4. So how many fours we have? 1, 2, 3, 4, 5. What it will store? 5, 4. Okay, this will store. And so how many 4 we have? 5, 4. So it will store 5. And what is that value? 5 times 4 is 5 times. Identical values at the beginning of attributes are left out. Instead, a value and the number of its occurrence are stored only once. Isn't it? Now, what is next data? 3. Then we have a 2. Then we have a 5. And how many 6 we have? 1, 2, 3, 4, 5, 6. 6, 6. Now, how many 7s? 1, 7. How many 8? 3, 8. And after that, we have a 9, no record. So this way, data is compressed in a prefix encoding. So this is, I would say, this is our uh, uh, OCCORR. This is our occurrence, and this is value. So this is how prefix encoding works. So guys, I told you, once you will understand this format, how this format gets converted, then you will understand this prefix or sparse encoding, whatever encoding I'm going to discuss. So you can watch my previous video and then you will be able to understand. Okay, now let's see what is our sparse encoding. Okay, so let me copy this same data. We assume that same data is stored, and oh, sorry, what I did, let me copy this, control C, control V. Let's see how same data gets converted using sparse encoding. Let me delete this. There's no use right now. So what sparse encoding says, the individual records from the value with the most occurrence are removed, which means most occurrence I can see 4, 4, 4, 6, 6, 6, 8, 8, 8. So these are values that will be removed, and the position of this vector, these entries are stored in a bit vector. Now, what is bit vector here? So what will happen? Let's see by example. What it will do, it will create again, for example, if I copy it, if I copy and paste here, what will happen? It will remove all these four. So for the better understanding, let me change this data. For example, we have a 4 here as well. Instead of 6, let me show you. Then you will understand. Again, this is 4, 4, 4. So as per the definition, individual record from the value which with the most occurrence. So most occurrence is 4. We can see that. So what will happen? It will remove 4 and it will store in a bit vector. Sorry, sparse encoding. Okay, and rest of the values like 3, 2, 1. Again, so look at the definition. It has removed 4. It will store 4 in a sparse encoding. Now next data is 3, 2, 1, then 5. Again 4, 4, 4. That will be removed. No 4, 4, 4. Instead, it will come now 7, 7. Again 4, 4, 4 will be removed. Now 9, and rest of the data will be deleted. So what happened? Instead, but how you will find out, because your actual data is this, but now how would you know that the data from here is has been removed? So the position of these entries are stored in a bit vector. So what will be the bit vector for this? What it will create? So for the above data, it will create a bit vector which will store actual position of this record. So whatever data has been removed, for that it will use encoding process 1. So we have how many times? 1, 1, 2, 3, 4, 5 times. 1, 2, 3, 4, 5 times. And data which has not been removed, which is actual data, for that it will store 0. So 3, 2, 1, 5. Again 4, 4. So it will store 1, 2, 3, 4, 5. For 7, 7, it will store 0, 0. For again 4, 1, 2, 3. For 9, it will store 0. Now, comparison the definition with the example. The individual records from the value with the most occurrence are removed. So most occurrence was 4, 4, 4, 4. You can see everywhere 4. So it was removed. Instead, the position of these entries are stored in a bit vector. So this is our bit vector. So this is the technique which use um, sparse encoding for converting data into which use technique data for conversion. Now next is cluster encoding. So what is cluster encoding? So let me paste, if I can. Yes, I can paste it. Now let's see what is cluster encoding. It uses data blocks of 10, 1024 values for each. Only block with different values are comprised. Block with different values are comprised by sorting only the value. Information on the compressed block is then stored in a bit vector. Again, it talks about the bit vector. Now we have understood how bit vector actually stores the position of these data. So now let's see how cluster encoding works. So let's create one hypothetical data, and we assume that this is stored in a memory. So let me design one table, new table. So insert new table. For example, let's say, for example, this, and let's store data. So for example, 5. For example, as I said, we assume that we have a data in a column, and that data can be anything, any column. We have a lot of columns in our table. So uh, in a main memory, as I said earlier, and we know that data is stored in a column format, and data is converted in a column format, and then it is stored in a main memory. So this is our main memory. What is it? This is our main memory. This is our main memory. So this is our main memory. But storing data in a main memory, some encoding process, conversion process uh, used internally. So I'm talking about those process. So we have seen like prefix encoding, sparse encoding. Now we are looking into cluster encoding. So what happens in a cluster encoding? Let's read out what definition says. Definition says it creates a block of 24 values for each. Only block with different values are compressed by storing only storing only the value. Information on the compressed block then stored in a bit. Understand that. Information on the compressed block. In a previous, what was that? It stores the position of these entries. Position of these entries. So actual position. What is the actual position? So actual position is stored in a bit vector. But in a cluster, it stores this into bit vector. So let's see how it works. So let me create 1, 2, 3, 1, 2, 3, 6. Let me insert one more table, actually one more row with column, for example, SS7. There can be n number of column for n number of columns. Yes. For my example, let me create this. This will not work for understanding purpose. Need little bit big structure. Then I can show you. So what happens in a cluster encoding is it uses the data blocks of 1024. For example, if I divide this data blocks into 4, this is our 455, then 2, so what will store? What it will store actually? It will store 5, then 2, then 1, 2, 2, 5, then 3, then 3 once, then 1, then 5, 4, 3, 2. It will store this. So you can see we have our 24 columns here, and now data is stored in just 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 in a 12 column only. And for this, it creates a bit vector. Let me show you. For this, it creates a bit vector. So let me insert a table for bit vector. Let me insert table for bit vector. So this is again, it will be the same, like not table required. We need to in a bit vector, it will store 1, 1. Why 1? 1 indicates these values has been replaced with the single values. So 5 has been replaced because we had a 4 times 5, and that has been replaced with 1, 5 one time. So for that 1. Same way 2 was 4 times. So for 2, bit vector will store 1. It indicates that 2 has been replaced with single values. Now 1 has not been replaced, 2 has not been replaced, 2 has not been replaced, 5 has not been replaced. So for that, it will store 0. Again, 3 has been replaced because 3 was 4 times. If I look at here, 3 was 4 times. So for that, it will store 1. 1 has been replaced. Yes, 1 was again 4 times. So for that, it will use 1. 5, 4, 3, 2, 1. It has not been replaced. So this way it will convert. So you can see the difference. Cluster encoding stores this value, but in previous encoding, sparse encoding, it stores bit vector stores position of this. So this is the difference you can see here. Now we have an indirect encoding. So for indirect encoding, let me create another structure. So let me insert a new table for this. So this table actually represents your memory here in my video. So this is a column store, and actually this is a memory representation. For making you understand, I'm using word table, but this is actually a memory representation technique. Um, so this way we can represent how memory stores actually data. Let me arrange this picture. It will be easier for you to understand. And I need some space here as well. And let me duplicate this. So what I'll do, I'll delete this. Need some space because this is this will take a little bit of space for making you understand. So for example, this is our what is main memory. This is our main memory. So we assume that we have thousands of records in my table, and if you look at the picture, so there might be one record in a position of 200. I'm taking new example. Mm, for example, one record at the position of 200, one might be at position 2. What happened? One record which is at position 2. There might be any data has been stored, but this is I'm showing you example of uncompressed data. One at 196, again one at 20 position, again at 20 position. Let me use two character values that will store easily. So 21 position, then again 2, then again 21, then again 20. So it let me read out. It also uses data block of 102 values for each. So let me create data block of uh, size of 8 character or 8 blocks. So this is our 8 blocks. This is our sorry. This is our 8 block. Another data of 8 block. And I'll create another of 8 block. Not possible to show 1024 it's not possible to show you 1024 size of block, so just I'm showing you block of 8. So let me change its color, so it will be visible to all of you. So this is of block size 8. Same way we have a data like here 19, 1, 3, 4, 5, 6, 7, 8. Again we have a data of size 31, 32, 31, 33, 31, 32, 30, 30. So you can see here we have a data. So this is 20 to 19. You don't get confused because this is the column position, actual position. So what actually it does, actually it creates for every block a dictionary vector is created. This is our uncompressed data. For example, this is my uncompressed data. Uncompressed data, which is actually visible to us. So there might be in a 20 position might be some value, and for a column, for example, might be name, location, address, amount, anything can be there. It's a one column. I'm just taking example of one column of a table, and that column stores data into main memory using some encoding process. So based on the data, based on the nature of data, it uses encoding process. It might be direct encoding sorry, indirect encoding, cluster encoding, sparse encoding, or prefix encoding, run length encoding. It can be any kind of encoding, but each encoding works differently and converts data in a different way, different process. So I am discussing this. So there might be situation we have 100 columns, 200 columns, or 500 columns, and I'm just taking example in the between of memory, like some 20 position might be, for example, country is saved. So for 20th position might be New Zealand is saved. Ninth position might be Canada is saved. At second position might be Atlanta or America is saved. So any value can be there in a position wise in a column. So what actually, if you look at the data closely, we have a 20 to 19, 20, 21 to 21, 20. I can see data is repeating. So what it does, it actually creates a dictionary encoding. So what it will create inside? Let me create one table here, a table with two columns, and how many identical entries? One, two, three, and four. One, two, three, four. It will create dictionary vector. So it will create dictionary vector. For example, let say this is column country. con and its position. So there might be any values can be there, this is our 20. So if I sort it, so what will happen, 2 will come the first, 2 will come the first, then after 2 19, and after 19 20, and after 20 it will come 21. So after sorting, as I said earlier, dictionary vector stores only identical data. So our identical data in this block is only 2 19 20 21 in a sorted order. So position of 2 is 1, position of 19 is 2 in a dictionary vector, in a dictionary vector position of 20 is 3, and dictionary vector is 4. So this is the dictionary vector. What is this? DICTI. And we know about dictionary vector is, dictionary vector stores only identical records in a sorted order. So in a sorted order, identical records will be this. Same way it creates for every block, but it checks whether data is being repeated. Here we can see we have only 30, 31, 32, and 33, and we can see 30 is repeating. First position will be 30, then 31 identical value. If I talk about an identical, again is 32 will be here, and 33, and the position will be the 1 2 3 4 for this block, for this block, and for this block. But for this block, it has it database finds that no duplicate values. It means no duplicate value, it means no dictionary needed here. So indirect encoding, what happens, each data blocks, for every blocks a mini dictionary like dictionary vector is created. So guys, I think you have understood this, what is dictionary vector, how dictionary vector is created for these values. And after creating a dictionary vector, it creates the um, creates the compression. So what will happen, for example, let me take one. So after, what will be in indirect encoding, what it will store after that. So first position is 20, 20 is 3, 20 is 3. Now second position is 2, 2 is at the first position in a dictionary vector, then 19, 19 in a second position, then we have a 20, 20 we have at 3 position in a dictionary vector, and 21, again 21 at the fourth position, and what is 2, 2 at the first position. 2 at the, and 21 again at the fourth position, and 20 at the third position. Third position. Okay, now for that we have no compression, so 19 will be here. So let me down the character size. And for this block we have no compression, no duplicate data. So what will happen? It will store the same records. 19, no compression. 1, 3, 4, 5, 6, 7. And for that again we have a 31 at the position of 2, 30, 32 at the position of 3, and 31 at the position of 2, and we have another value is first value is 31, and 31 at the position of 2. First value is 31, 19, 1, 3, 4, 5, 6, 7, and this should be the 8. Now we have a 31 at the position of 2, 32 at the position of 3, 33 at the position of 4, 4, and so on. Because of space, I don't have sales available here for showing you, but you can understand. I think you have understood what actually happens in indirect encoding. So indirect encoding uses the data blocks, and each block creates a mini dictionary that's similar to dictionary vector encoding, and it converts only those blocks which has the data which is repeating, and for that it creates the dictionary vector. So we have understood indirect encoding. Now we are left with last one, that is run length encoding. So we have discussed cluster encoding. We have, let me delete this. I need some space here. Now we are left with run length encoding. So let's understand what is this run length encoding. So for this, let me create one table again, and for example, we have 20. So we know you've understood that what is this table. Actually this is a main memory. So what it says, identical successive values are combined into one single data value. This value is then stored only once its together with number of its occurrence. So for understanding this practically, let me create hypothetical data, and we assume that we have a column, we have a multiple rows, multiple columns, and in that column there are multiple records which is being repeated, and it might be, for example, we have a name column, and we know that we have a name which can repeat in a column for an organization, in a bank, anywhere. So for example, our uncompressed data is like 5 5 5 5, then 4 4 4, then 6, 6, 6, then 7, then 7, then 7, then 8, 8, 8, 8, 8, then 9, 9, then for example 1. So hypothetical data I have taken just for the example. So after sorting, this will be the structure of your data. There might be name for like Sumit, 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 Vivek, Vivek, Vivek. This kind of data will appear after sorting. So we assume that after sorting, this is the dictionary representation after sorting it, raw data. Now, what actually happens in a run length encoding? The value, successive values are combined into one single data value. So we have a repeating record 1, 2, 3, 4, 5, 6, and 7. For example, we have a 7. Okay. So if I look at the identical record, it's a 5, and it's a 4, and it's a 6, and it's a 7, and it's a 8, and it's a 9, and it's a 1. So there might be multiple entries. This is, for example, I have just created random numbers. So this is the current situation. For example, if we need to find out this position, let me copy and paste here. For example, this is our position. For example, it says 0, 1, 2, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, and 19. For example, this is the position of data in a memory. This is the position of data in a memory. Come down here. Now, if I look at this is our data. This is our identical data. We can see our values. And now it creates one more structure internally. Start position. Start position. Let me copy this. So start position of 5 is Control C, Control V. This is our position. So start position of 5 is 0. From 0 to 2. Start position of 4 is from the 3 here. Now start position of 6 is from 6 itself. That is correct. Start position of 7 is from 9. Start position of 8 is from 12. And start position of 9 is from 17. Start position of 1 is from 19. So this way run length encoding works. So now let's read out the definition. What definition says: identical successive values are combined into one single data value. You have seen that it's a one single data value. This value is then stored once together with number of its occurrence. So here from 0 to 3 total number, can we find out how many numbers are there? So this is how run length encoding works. So now we have seen all the compression techniques, which are prefix encoding, sparse encoding, cluster encoding, indirect encoding, run length encoding, and dictionary encoding. And dictionary encoding, we know that this is the default encoding process in SAP HANA. So based on the cases, internally database uses these compression techniques, prefix encoding, for example, for the very frequent value at the beginning of the attribute vector, then it selects a prefix encoding. Sparse encoding, if very frequent values are occurring at the multiple levels or several levels, several positions, so then database selects the sparse encoding. Same way cluster encoding. So if many blocks with the same value, with the one values are there, then cluster encoding comes into selection process in a database for the compression purpose. And indirect encoding, if we have a many blocks with a few different values, so then in that situation indirect encoding comes. So run length encoding comes when few different values and consecutive identical values are there, then run length encoding um, gets selected for the compression purpose. So these are the various techniques which SAP uses for the data compression. So in my next topic, I'll discuss about partitioning. So what is partitioning and what are the partitioning available with SAP HANA? So guys, SAP HANA uses only horizontal partitioning, and I'll discuss again horizontal partitioning in a same way in a detail how actually it works, and how actually partitioning, what are the multiple types or various types of partitioning techniques we have for the horizontal partitioning. And for till today we have covered all these concepts, like software components in memory technology, data layout in main memory, and today I discussed about data compression technique in more detail, and we come to know what are the techniques, what are the process uh, SAP HANA uses for compression purpose. So in next topic, I'll show you how we access data without any index, how SAP HANA uses this technique, and I'll cover that partitioning part also in that session. And if you are not able to understand this part 4 video, then you need to watch out my previous videos. I have shared details how you will mm, uh, find out my all videos. So you have to just go to YouTube and you have to type SAPEX technologies. You will see this icon and SAPEX technologies. So I have shared multiple videos. These videos will be available, and every Saturday I'm trying to share one topic with all of you. So by the time, guys, go with it, and thank you for the time. Thank you. Take care. Now your questions, please.